Welcome to the 10th lecture of EEE 23 of Electromagnetics 1. This lecture is about plane waves. So everything that we have learned will now be tied together. Right? So let's recall what we have learned. Basically, every law in electromagnetics is summed up with these four equations that were summarized by Maxwell. You have your point form and your integral form. The point form here, this is Faraday's law. This law is Ampere's law with Maxwell's annotation. Right? This is Gauss' law for electrostatics. Sorry, Gauss' law for electric fields. And this is Gauss' law for magnetic fields. Okay. Now consider the case that we have a sinusoidal electric field and magnetic field. Sinusoidal in time. Basically, your electric field is at one point, let's say here, okay? And initially it's in this direction, but it changes with time in a sinusoidal manner. So at one point it's like this, and then at some point it will become like this. Okay. What will happen? A magnetic field actually is generated in the direction that is perpendicular. Okay, let's use the blue here. That is perpendicular to this point. Okay, this is because of the changing electric field that a magnetic field is induced. And if a magnetic field is induced, another electric field is also induced. Okay? So what would happen? They will eternally induce each other. So, okay, let's assume they are sine waves. Sorry, let's assume they are sinusoidal in time. They induce each other. So as you can see, they induce each other actually forever. And because of that, they kind of propagate in space. Okay? So they induce each other forever, and they propagate in space. And that's where our electromagnetic waves come from. If you have a time-changing source here at the middle, the electric field and magnetic field induce each other such that they propagate equally throughout the whole space. If you go far enough from this, source, if you're here, you're the observer, this spherical wavefront, since we know that the propagation is equal over all directions, if you go far enough, then you'll observe that this propagation is approximately planar. And that is our plane wave approximation. Alright, let's step back a bit. How did this all happen? What is the proof? First things first. Let's go back to Euler's identity. Since we're now dealing with time and sinusoids in time, these sinusoids have a phase and an amplitude. We can represent all sinusoids into phasors. So recall that. That's from your EEE 33. If we represent them in terms of phasors, our calculations become easier. Example. Okay, so let's just recall first. Your wave, which is a function of space and time, since we're assuming a sinusoidal dependence in time, then our amplitude is a function of space. And the time component is basically a sinusoid with a phase phi, which is equal to the real part of a complex amplitude multiplied to this function right here. Recall that this function can be broken down to its cosine and sine component. Okay. And if you look at what's inside of this real operator right here, it's this expression. Okay. This expression is the complex amplitude, and this is the uh, sinusoidal dependence. Excuse me. So this complex amplitude right here is our phasor. We will look at our electric fields and magnetic fields as phasors. To revert them back to the real domain, or the time domain expression, just get the real part of this whole function right here, and you'll be reverted back. Alright, so what is the effect of this sinusoidal and phasor notation to our Maxwell's equations? So recall that this first equation right here is our Faraday's law. So if we get the derivative of B with respect to time, okay, so recall. So the derivative of B, since we assume that B is sinusoidal, then this function, this magnetic flux density function, is some B as a function of space, let's say R, okay, times e to the j omega t. Okay? This B of R is the complex phasor form of your magnetic flux density. If you get the derivative of this is just dependent with space, so it will be factored out of your differential operator. Okay, so that's B of R. And the derivative of this is j omega e raised to j omega t. And this B of R times e to the j omega t, that's your original expression for your magnetic flux density. Okay? Therefore, this derivative becomes j omega B of R. Or sorry, j omega B. That's why Faraday's equation or Faraday's law becomes this expression right here. Same operation can be done to our electric field, and Ampere's law becomes this equation. Okay, so let's consider a special case. So we want to prove that our electric field and magnetic field actually propagate. So what is the special case here? Let's use our plane wave approximation. So that is at this region. And at this region is very far, it's very far away from the source. Therefore, if this is free space, there is no conduction current anywhere in this region as it propagates. No conduction current, and there is no charge anywhere in the region. Our Maxwell's equations becomes this. There is no conduction current and there is no charge stored. So with this, let's consider the first two. Okay? And we just want to relate our electric field intensity to our magnetic field intensity, E and H. So this B is equal to mu H. This D is equal to epsilon E. That's why you see these two equations right here. If you take the curl of this first equation, so you're taking the curl of E, that is equal to negative j omega mu times the curl of H. This j omega mu are just constants. Therefore, in the curl operator, they are just gonna be factored out. And the curl of H here is equal to this equation right here. So this curl of H just becomes j omega epsilon times E. Simplify that. J times J is negative 1. Therefore, this negative becomes positive. The curl of our electric field intensity is equal to omega squared mu epsilon E. So from here, we'll use an identity, the triple product identity. So don't ask me to prove it for you. I'll leave that to you. So this is your triple vector identity. If we get the curl of E, then it follows this form. It's the first is, this is the gradient of the divergence of E minus the Laplacian of E. Okay, so this is the Laplacian of E. So remember what Laplacian is. So if we consider this term right here, this is the divergence of E, which will be 0. Why is it 0? Because the divergence of D is 0. Mainly because there are no charges in free space. There are no accumulation of charges in free space. So we're considering that case. So now this omega squared mu E, sorry, that's not right. Let me change that. Omega squared mu epsilon E is equal to negative of the Laplacian of E. So you transpose that to the other side, you'll get this equation right here. And this is called the wave equation or Helmholtz equation for electric field. So notice that, okay, recall that what the Laplacian is. The Laplacian is a second derivative with respect to space. This omega squared mu epsilon is a constant. So it's a second derivative with respect to space plus some constant times E equal to 0. This results into a sinusoidal expression. We'll get to that later. So let's look at, if we apply this operation in our magnetic field, we'll also get the same equation. Okay. So it seems like the electric field and the magnetic field have the same properties. What do we say? What do we mean when we say property? They are both of the same wave, and they also produce the same constants here. We'll call it k squared, sorry. We'll call this k squared. And this is actually the wave number, or the propagation constant, which is given by this equation right here. So in terms of wave number, Helmholtz equation becomes this and this. Right? So we're already considering Laplacian here. We're considering the propagation in all directions. Let's look at the case for plane waves in a lossless medium. So a lossless medium is where we don't have any conduction current and we don't have accumulation of charges. So that's what we solved earlier. So let's also consider only propagation in a single direction to simplify our Laplacian. So if we consider propagation in the z component, okay, our electric field will be left with an x component. So let's assume that the electric field only has an x component. What will happen to the equation? If the electric field only has an x component, the Laplacian of an x component will result into this derivative right here. So it will be a differential equation in the z direction. So we apply our methods to solve a second order differential equation. Okay. The result of this equation is this. So let us examine both terms. One of the terms, it has a negative exponent, and the other has a positive exponent. Since these are phasors, we can convert them to the time domain by multiplying e to the j omega t and getting the real part. So it turns out that the real part is this for the first term and this for the second term. So this term right here travels along the positive z direction. And this term right here travels along the negative z direction. Okay? So that means if we have some source of electric field that propagates, or sorry, that changes in time in a sinusoidal manner, this change in time of your electric field actually creates a forward propagating electric field and a backward propagating electric field. So one travels in a positive z direction and another travels in the negative z direction. So what are the properties of this traveling wave right here? First thing that we want to know is how fast it travels. We can use what we call the phase velocity for that. So consider a point on the wave. Let's say we're looking at the peak. This wave travels some distance x with respect to time. In this case, it travels along the z direction. So our point here traveled some distance delta z after some time t. So we want to know delta z over delta t. Okay? So delta z over delta t, or plainly, the derivative of z with respect to time. So consider this point. This point is actually a constant phase on this traveling sinusoid right here. If this is a constant phase, then this omega t minus kz, since this is the phase inside our cosine function, this is constant, then if we're tracking that phase, then this omega t minus kz is also constant. Rewriting that, getting we want to isolate z. Okay, so in this case, z is omega t minus some constant, let's say k. Not k, let's say it's alpha. Omega t minus alpha over k. So if we take the derivative of this with respect to time, we can see that since this is constant, it won't matter. The derivative of z with respect to time becomes equal to omega over k. Right here. And this is called the phase velocity. So the phase velocity is omega over k. It just so happens that it's equal to 1 over square root of mu epsilon. Okay, so remember that k is the propagation constant, which is equal to omega square root of mu epsilon. So substituting that, you get the phase velocity equal to 1 over square root of mu epsilon. In the case of free space, mu becomes mu sub 0 and epsilon becomes epsilon sub 0. This phase velocity becomes 2.998 times 10 to the 8 meters per second. And this is actually the speed of light. And this is how early on in early physics, when there are still no, what do you call this? There's still no fancy equipment like our fast cameras. This is how they measured, quote unquote, the speed of light. They did not really measure it. They just reasoned with it. They proved it using Maxwell's equations. So this is how they got the speed of light. So it's that fast. Alright. So the next property we're looking at is the wavelength. The wavelength is, you already know this, the distance between two phases within the same wave. Okay? So the distance between two phases with the same value. Two phases with the same value. So this distance here is, well, if we're gonna have a what do you call this? If this has almost the same phase, so that means their phase difference here, since this is a sinusoid, is equal to 2 pi. Okay? So this assumes, so we're looking at a fixed point in time, therefore t is constant. This phase here is omega t minus kz, and this phase here is omega t minus k times z plus some value delta. Lambda. This lambda right here is actually the wavelength, since it's the difference in space. Okay, so simplify that, you get k lambda is equal to 2 pi, and lambda becomes 2 pi over k. Since k is equal to omega, Vp over omega, k is omega over Vp, then this expression becomes 2 pi Vp over omega. And finally, since omega is equal to 2 pi f, as you know, 2 pi f, this lambda is equal to the phase velocity divided by the frequency. Basically, the wavelength of the wave is dependent on the phase velocity and the frequency of the wave, or the frequency of the excitation of our electric field. If we force a single point in space to have a an electric field that is sinusoidal in time with some frequency f, the result of the propagation from that sinusoidal electric field has a wavelength that is dependent on the frequency. Okay? So the higher the frequency, the smaller the wavelength. So this is the propagation in our lossless medium. Okay? So to sum it all up, as mentioned before, the electric field and the magnetic field are dependent of each other. So knowing one of the two will solve the other. Assuming that we know the electric field, okay, you can apply Maxwell's equations, it can solve for the magnetic field. Okay, so this is how we solve for the curl. It will only be left with z. Okay, and it results in this expression of your magnetic field, and this k over mu omega mu right there is what we call the intrinsic impedance. So why is it measured in ohms? So it's impedance also, because recall your electric field here, it's volts per meter. Your magnetic field here is amperes per meter. So volts per meter over amperes per meter becomes volts per ampere, becomes ohms. So this is the intrinsic impedance. If we're looking at the impedance of free space, just substitute mu and epsilon here, mu naught over epsilon naught. It becomes 377 ohms. So this is the free space impedance. Therefore, our wave looks like this. The electric field and the magnetic field are orthogonal to each other. That's what I told you earlier. And it's also orthogonal to the direction of the propagation. So if this is the z-axis, right here, that's the direction of propagation. Our electric field is sinusoidal in time, initially pointing upwards in the x direction. And our magnetic field follows, initially pointing in the positive y direction. Okay? So the wavelength is dependent on a snapshot in time. This is our wave, a snapshot in time. And it's dependent on the distance between two crests of your wave. Okay? And the property that all these electric field, magnetic field, and the direction of propagation being orthogonal to each other, okay, this is a property of what we call a transverse electromagnetic wave, or TEM wave. So a transverse electromagnetic wave has a direction of propagation that is perpendicular to both the electric field and the magnetic field. Okay. So not all waves actually in certain mediums have a transverse electromagnetic propagation. Okay. So if you take higher electromagnetic courses, you'll see that actually there is a transverse electric propagation where the magnetic field is not perpendicular to the direction of propagation. And there's a transverse magnetic propagation where the electric field is not perpendicular to the direction of propagation. But that's already for some other course. Okay, so I'll end the first part of the lecture here. If you have any questions, do not hesitate to comment in the comment section below. Thank you for listening. I'll see you when I see you.